Welcome to this presentation on impulse and step signals. The outline is as follows. We will present the concept of discrete time impulse signal, discrete time step signal, relation between them. A unit step sequence denoted by 1 of n is as follows. It takes the value 1 from time instant n equals 0 onwards, before that it is 0. So, this n denotes the time when it takes the value 1. In signal processing courses, they use the symbol u here to indicate unit step sequence, but in a control course u is defined as the input, rather u is reserved as an input. So, as a result, we would like to use the symbol 1 here to indicate unit step. This is a doubly infinite series. It starts from minus infinity, it goes all the way up to plus infinity. So, I call it a doubly infinite series. So, 1 of minus infinity onwards, dot dot dot, 1 of minus 2, 1 of minus 1, 1 of 0, and so on all the way up to 1 of plus infinity. And remember, only from n equals 0 onwards it takes the value 1, before that it is 0. That is how this function 1 of n is defined. So, when I substitute this, it becomes zeros all the way up to n equals minus 1, that is up to this point. From n equals 0 onwards it becomes 1. It takes the value of 1 from the time the argument becomes 0. The argument, that is n equals 0, becomes 0. Next, we will consider the basic discrete time signal impulse. We will denote it as delta of n. As in the previous slide, as in the case of unit step, we put this inside braces, indicating that we are talking about a sequence. That sequence takes values 0 everywhere except when n is equal to 0. When n is equal to 0, it takes the value of 1, and we say that when the argument n becomes 0, it takes the value of 1, and that is the unit impulse sequence or unit sample sequence. Okay. This is also a doubly infinite series starting from minus infinity all the way up to plus infinity, and it is defined as follows. When the argument is 0, it is 1, everywhere else it is 0. So, it becomes zeros everywhere except at n is equal to 0. So, you have to remember it takes the value of 1 at the time the argument becomes 0, that is n is equal to 0. Can we get impulse sequence from a step sequence? That is, the answer is yes. Here is one step sequence defined. Here it is 1 of n. Let us consider a time shifted version of it, 1 of n minus 1. So, as a result, when the argument becomes 0, it takes the value 1. The argument becomes 0 when n minus 1 is equal to 0, that is n equals 1. When n equals 1, the argument becomes 0. So, as a result, from n equals 1 onwards it becomes 1. Supposing I subtract the second sequence from the first sequence, then you see the second, third and fourth entries become 0. In fact, all future entries become 0 except at n is equal to 0. So, we get the result. You can see that it is nothing but delta of n, that is delta of n is equal to 1 of n minus 1 of n minus 1. It is also possible to get step sequences from impulse. How do we do this? It is straightforward. Remember, 1 of n takes values of 1 from n equals 0 onwards. This one takes the value only when n is equal to 0. This is only when n is equal to 1, only when n is equal to 2, and so on. You write it all the way up to infinity, you see that the right hand side is equal to left hand side. So, you can write it using this formula. This is a very important result that we would like to derive in this slide. can we express an arbitrary sequence u through delta. So, u of n is an arbitrary sequence, it takes the value from minus infinity to plus infinity, and each of these is a scalar. We will split them into individual components. For example, for component u of minus 1, I will say u of minus 1 is not 0 at the same time instant, but everything else is 0. For u of 0, you take everything else 0 except at this location, which is 1 shifted from here. Similarly, for u1, I do the same thing, I shift it by 1 and I write this. So, each of these is a doubly infinite sequence, but with only one non-zero entry. So, if I add this component wise, I will get this. Now, what I want to do is, I want to let us take this only, and here I want to, because it is a scalar, I can pull this out, u of minus 1 into all 0 except 1 here. This 1 comes at time instant n equals minus 1. So, it is a doubly infinite sequence with only one non-zero entry, that is 1 at time instant n equals minus 1. So, what is this sequence called? So, that is nothing but delta of n plus 1, because when n is equal to minus 1, the argument becomes 0. So, it takes the value 1 at that instant, namely at n equals minus 1, which is indicated, which is here, which is also of course indicated here. What about this? This should be u of 0 into delta of n using the same argument. This is u of 1 into delta of n minus 1. So, I can write it in the form of this formula. Do this for starting from minus infinity all the way up to plus infinity. Remember a nice thing here, if I add these two, I get this n here. N plus 1 minus 1 is n plus 0 is n minus 1 plus 1 is n, and so on. Here of course n minus k plus k is n. So, one can think of this as a vector decomposition with delta playing the role of a unit vector. Along this delta, the component is u of minus 1, along this it is u of 0, along this it is u of 1, and so on. Remember the sum of arguments formula, if you add these two, you should get this argument. If you remember this right, you will always get this expression correct. This formula here is an extremely important formula. We will use this to derive the convolution result. We will keep seeing a formula of this type again and again. So, let me stop here. Thanks for joining.